Okay, so on Friday we had the tutorials. So we had a look at some of the questions coming off of the Euclidean algorithm. You really do need to ensure you're able to operate the Euclidean algorithm, that you know how it works, that you don't get muddled up in the middle of it, and you've got a clear understanding of how it proceeds. Both in the forward direction, where it defines the greatest common divisor of the two numbers, and then when you're working back through the integer divisions, where you're generating the linear combination of the intermediate pairs and ultimately the original pair, the linear combination of them that gives you the GCD. So it's the two things that it does. And that knowledge of the existence of the linear combination of the two numbers that gives you the GCD, that's important from a kind of theoretical point of view. We use the fact that that linear combination exists a lot of the time in our arguments around divisibility in prime numbers. And we also use it in a practical sense, as you've seen in some initial cases with John. Generating the coefficients for the linear combination is one way to calculate the multiplicative inverse of an integer modulo some other number. Okay? Now, you'll see in chapter 4, I believe it is, chapter 4, we'll be doing a thorough study of the congruence relation and modular arithmetic fairly soon. John has started using it all right in cryptography. We'll be doing a very careful, thorough theoretical study of it. Okay, so that was the tutorial. I'll be later today, I'll be releasing the solutions to all the chapter 2 exercises. So you can use those as a good resource for checking your work on that. But I would encourage you to tackle the questions head on first time yourselves, because that's when you can do a lot of the learning by trying to figure these out on your own. So. Okay then, so we started chapter 3 the last day. And we started it, okay, we met the definition of a prime number, okay, a number bigger than 1, which has no factors other than itself and 1, an integer. This is the first few prime numbers, 2, 3, 5, 7, 11. We had already proved earlier on that every integer factors into primes, okay. You can do that using pre-prime induction. It more or less just folds out the definition of a prime number. A number that is not prime, by definition, factorizes as the product of smaller numbers. And if those aren't prime, by definition, they factor. And so you keep factoring everything until you've got the original number written as a product of prime numbers. It's the proof there in Theorem 3.1 is presented formally in the form of proof by induction, but it really is just that idea. Keep factoring the number until you can't factor it anymore, then you're looking at the prime. At a prime factorization. But still the question floating in the air, is it the prime factorization? Are prime factorizations unique? You discover by investigation that they are unique for any particular prime number that you try and factor, for any particular integer you try and factorize it, you'll only be able to factorize it into essentially one product of primes. You can mix up the order of the prime factors, but you can't never actually find a different set of prime divisors of a given number. It always just has one unique set of prime divisors. But we don't have a proof of that yet, but we will in a few moments. Okay? And then, to finish the review of last time, we looked at this proof last time, which is kind of the jewel in the crown of beginning number theory, is that the proof that there are an infinite number of prime numbers. Okay. This comes out of the definition of a prime number and the basic concept of divisibility. The proof proceeds by contradiction. So we start the argument by supposing that the conclusion is false. Okay. We're going to prove it's true, but we suppose it's false. If it was false, then there would be a finite set of prime numbers, P1 over Pn. Okay. So that would be all of the primes there. But if you've got all of the primes at your disposal, you can multiply them all together and add 1. That gives you another integer, capital M. And we've already proved that every integer factors into primes. So Either m is a prime number or it has a smaller factor which is a prime. That's by theorem 3.1. Now we know it isn't prime itself because it's bigger than all of the primes. And we've supposed falsely that there are only a finite number. So it can't be a prime itself. Therefore, it must have a prime factor. So one of these pi's must divide m. So it must be that one of the primes, or it's called pj here, one of the pj's divides m. But of course, pj also divides this product of all the primes because it is sitting there as one of the factors in that product. So pj divides these two numbers, so it certainly divides every linear combination. In particular, this simple linear combination, m minus the product of all the primes, which we know to be 1, okay, because that's how m was defined. So then we're in the situation where we've got a prime pj dividing 1. And the only positive number that divides 1 is 1 itself. So we're forced to the conclusion that this prime is actually equal to 1. But that's a contradiction. Okay, it's nonsense. Okay? Primes were defined to be numbers bigger. So you can't have a prime number dividing 1 equal to 1. So this is a contradictory conclusion. It contradicts something we know to be true. So there must be a problem in the argument that led to it. The argument was okay. Every step was perfectly logical except for the very first one, where we supposed that there was a finite number of problems. That's how proof by contradiction works. Okay. You make a well-chosen, what you suspect to be false assumption at the beginning. You argue logically and mathematically from there until you reach something which is clearly false. Okay. And you can't prove false things, so the problem must be in that original assumption. Okay. We could also look at a slightly, okay, I'm going to pause for questions. So that was a quick run through the last introduction to chapter 3 we did. Definitions. Any questions on your mind at the moment? In particular about that proof and the argument used there? So everybody should be able to give a rendition of that proof just at the drop of a hat. It's like knowing the national anthem or the main prayer in your religion. You know, it's just something that should be there, accessible to all the time. And you know, if one of your relations or friends who has no knowledge about mathematics asks you what you study, what you do, you know, prove to them that there are an infinite number of prime numbers. It's not too technical an argument. They have this wacky idea to outsiders of proof by contradiction, where you start by pretending that the thing you're trying to prove is false, which does sound really weird to, you know, I hesitate to say it, to normal people out there who aren't like us. But it's a perfectly acceptable idea to us. But this, you know, everybody should know this very, very well. Not least because if you look at past exam papers, quite frequently I do ask you to prove it in an exam because it's so important to results. Okay. But before we move on, so in this lecture we're going to move on from it and we're going to prove our fundamental theorem of arithmetic. Finally, prove the uniqueness of prime factorization. But first, I just want to give an alternative view. So this is an alternative view on Theorem 2.2. Now I'm almost going to present the same argument to you again, but it's a useful way of thinking about it. Instead of thinking about it as a proof by contradiction, what we'll do is we'll present the argument. So we can present the argument as a constructive algorithm for generating primes. So we can specify it as a computer program, when you set it running, it never stops, and from time to time it spits out a new prime. And whenever it spits out a new prime, while it might take a long time to produce the next one, it will produce the next one in a finite amount of time. And so its computer program is never going to stop, and it's always, in a finite amount of time, it's always going to produce another prime. And the gaps of time will get longer and longer, but it will always produce another prime. And it's going to run forever, it's going to never stop, so that proves that there's an infinite number of primes. Okay? And it's more or less the same argument. Okay? So it begins by saying, here are some primes. And, well, all you really need to begin the argument is just one prime, but, you know, here's a list of a few primes. Okay, 3 primes, 2, 3, and 5. So we multiply them all together. So let's say that's our P1 up to Pn. So you've got, at the intermediate stage, you've got some primes. You multiply them all together and add 1. So you produce m, which is the product from 1 up to n of the primes you've already got, plus 1. So we're not doing proof by contradiction here. We're not assuming that Pn's are all the primes. They're just some bunch of primes that we've accumulated at a certain stage. We multiply them all together and add 1, just as we did in the proof of Theorem 3.2. Then either n is prime itself, or it has a prime factor, and I'm going to call this q. And because of the same argument in the middle of Theorem 3.2, that if this prime factor q was one of these p's, then it would have to divide 1, and that's a contradiction. So by that same argument, in Theorem 3.2, q is a new prime. Okay, it can't be one of the pi's. Okay, so either m is a new prime, because m is bigger than all the numbers you had, or m has a prime factor which isn't on your list already. Okay, so you can add q, add m or q as appropriate, depending on which one's prime. Add m or q to our list of primes. And then you've got a longer list, and then you go back to the top. Okay, I know it doesn't look like a computer program, but essentially that is a description of the algorithm. Okay, nothing's ambiguous. You've got prime numbers, you've got a bunch of numbers, multiply them all together, add 1. This new number, you can inspect it, you can discover its prime factors. Either it will be prime itself, in which case great, you find a new prime, you can add it to your list. Or if it's not prime, when you look at its prime factors, any of its prime factors will not be any of these numbers. Because if they were, they would have to divide 1. Yeah. So in either case, either n or one of its prime factors, you've generated a new prime, which you can then add to your list of primes and then just repeat the whole process. Okay? And there's nothing there in that description that will fail at any point. Okay? Now, so it'll go forever, and each step there is achievable. If you've got a large number, you can discover its prime factors by just trying to divide it by all the smaller numbers. So there's nothing stopping any operation there. There's nothing there that says it's going to stop. So it's going to keep going without end. Okay? And it will always generate a new prime number. Now it'll take longer and longer to achieve this factorizing step, because as the numbers get bigger and bigger, it takes longer and longer to discover their prime factors. It can always be done if you have enough time to wait around. But you will run into process will slow down, but it'll never stop. And it's useful just to see that in operation a little bit, which we can do now. So I'll show you this in Sage, but it only uses very basic commands, and you could reproduce this in Sage yourself, or indeed in MATLAB, or in basically any other computer program. So you can start with your list of the few primes that you know about. Let's just wait for that to, it's just starting up Sage. So it'll run a lot quicker now. I suspect there's a command called product, which I can probably call on a list. Honestly, don't know. Return the symbolic product with respect to the variable m point. Well, let's try calling it on the list. Excellent. Okay, so calling product on the list simply multiplies together all the numbers. So we'll add 1 to that. So that's our number m, and we then factor m. Okay, in this case, m happens to be prime. Yeah. So we then do L dot append m, this new prime that we found. Okay, so back here, okay. So we'll look at our list. Our list is now longer. We've now got some more primes. Form this new number, 931, which is a product of all of those plus 1. Factor it. Okay, so we can see 2 new primes here, 7 and 19. Append means add elements to the end of the list. Oops, except you can't call it like that. Well, let's just take 7. Okay, 2, 3, 5. So we discovered we've made our list of primes longer, so we can go back to the start. There they are. Multiply them all together, add 1. Factor 6,511. Got a new prime, 17. Which is smaller, 7 and 17 were smaller than the 31 that we found. That's okay. So you can, nowhere is this process going to run into any problems, and it will never end. Ooh, we discovered 11. We didn't have 11 by now. Oh, let's take 1,000. What's that? 10,061. 10,061. Yeah. So you get the idea. 13. What is it? 13. Okay, so just running that process a few times, we've already discovered an interesting bunch of primes. Of course, we're missing lots of primes. I don't think this process will discover all of the primes, but it will keep generating at least 1 new prime at each stage. Okay? And you can just keep running and running and running. So that's another way to think about the Euclid's argument. Okay? It's normally presented as a proof by contradiction, but you can also present it in a much more constructive way. Here, we're specifying a process for building an infinite or a unending list of primes. Of course, all we have to do now is just put those few lines of code inside a for loop or inside a while loop, and like while true. So there's no condition to stop the while loop, and just let it run endlessly. And it will just grow that list L until eventually the computer runs out of memory and it stops. Okay. But in principle, the argument could continue without end. Okay. So okay, any questions or comments? So it's 2 different views on the same, essentially the same argument. One as a proof by contradiction, the other one has much more different flavor, specifying an algorithmic process. Okay. So that's enough on Euclid's argument for now. So now we approach our fundamental theorem of arithmetic, okay, which we've already introduced and commented. So the fundamental theorem of arithmetic talks about the existence and uniqueness of prime factorizations. For instance, 495 is 3 by 3 by 5 by 11. Okay? That's its prime factorization. Now, try as you might, you will not be able to produce 495 as a product of prime numbers in a different way. Trivially, you might mix up the order of the factors, 3 by 11 by 3 by 5. Okay. You might consider that a different product than the previous one, but it's not really essentially different. You just move the numbers around a bit. Okay. Apart from that, trivial difference. Yeah. But if you don't consider those as different factorizations, the fundamental theorem of arithmetic says there is only one way to factor any positive integer into primes. Okay. Now we haven't seen a proof for that yet. We haven't seen an argument for that. We might have a strong intuition that that's the case from looking at these small numbers. In the case of 495, we can prove it because we can just consider all possible products of primes smaller than 495. There's only a finite number of them. You can quickly run through all the products of them that are less than 495, less than or equal to 495. You'll observe that none of them are 495 except for this one, 2, 3, 5, and 11. So you can prove it in the case of that integer. But we don't yet have a good way to think, we don't have a good general proof idea that will work for all integers. Okay? So that's what we're going to do now. Okay? So the fundamental theorem of arithmetic, we normally see the prime factorizations written in general like this. So this expression here is just an example of one of these. So you've got your n expressed as a product of a power of p1 times a power of p2 all the way up to a power of some last prime pr. So the pi's are distinct primes. Okay, so each of the pi's are different primes. Emphasize that there. Yeah, distinct primes. The exponents alpha I are positive integers. Yeah. So the alpha I are, if we're going for the unique prime factorization, each of these alpha i's are strictly greater than 0. So we're not needless, you know. I mean, I could add in another prime by 7 to the power 0. Still give me 495 because 7 to the power 0 is only 1. Right? But 7 isn't really a prime divisor of 495. Okay? It goes in, it's just not present. So in this thinking here, we aren't including items like that. Okay? So we're only including the primes that actually divide them. Okay, we've already seen the proof that these things exist. That was theorem 3.1. Every positive integer can be factored into a product of primes. This didn't prove uniqueness. It just gave you an argument that says there is a factorization of n into primes. This is stronger. It says there is only one, essentially, factorization into primes. It does need to be proved. You can give examples of number-like algebraic objects where prime factorization is not necessarily unique. Now, we don't study these things in this unit, but these things are called algebraic or rings of algebraic integers. Its construction looks a little bit like the construction of complex numbers. You're taking every a plus bi, except this time the a's and b's are restricted to be integers, and the imaginary part always has a factor of square root of 5. Okay, this set of complex numbers, so it's a subset of the complex numbers, and it acts like its own little closed number system. If you multiply together numbers of that type, it always gives you an answer of that type. You add together numbers of that type, it always gives you another number of that type. So it acts like its own closed little system. But in this system, you can factorize 6 in 2 different ways into prime-like elements. Okay, you can write 6 as normally as 2 by 3. 2 and 3 are both elements here, so you can have a as 2 or 3 and b as 0. But you can also factorize 6 as this product here, which is also a product of elements from Z. Okay? And neither of 2 or 3 can be factorized any further. So here is an example of a related algebraic structure, an algebraic structure of number-like objects, certain complex numbers, in which prime factorization is not unique. So that even emphasizes more the need for a proof in the case of the regular integers. It's not enough to just say, well, we've got a feeling about addition and multiplication that kind of tells us the prime factorization is unique, because it's essentially the same operation of addition and multiplication that's going on in this system. But there's something about the selection of elements here that makes prime factorization non-unique. Okay, so we do need a proof of it. So let's go for it. So first we've got a preparatory lemma, which is lemma 3.4, which sometimes goes by the name of Euclid's lemma. Sorry, Euclid's lemma. And this is really a special case of a previous exercise we had. On the question 2 exercises, it was, the exercise 2.1, question 6, page 11. So this actually was one of the exercises in a more general setting. Okay, so this is an example or one instance of that previous exercise. Well, we'll go through the argument for it. It's nice. So this basically says let A, B, and P be integers, and P is a prime. Okay, in a number theory course, we reserve the letter P to denote prime. So you shouldn't use P to denote something that mightn't be a prime. It's a reserved letter. Okay, it would be strange to use it for something that isn't a prime in number theory. So Euclid's lemma says that if P divides the product AB, then P divides A, or P divides B. Okay, so if a prime divides a product, it must divide one of the factors. It might divide them both. Remember, this or isn't exclusive or. It could be that P divides both of them. But it must divide one of them. Okay? It must divide. And you can easily see that it isn't true if P is not a prime. So the fact that P is a prime is important, because if you allow P to not be a prime, you can easily construct a counterexample, couldn't you? Someone give me a counterexample to that, if P wasn't a prime number? If P wasn't prime, could you get a counterexample to this? So where the first number did divide the product, but it didn't divide either of the factors.
Say it's like P was 6 and A was like 2 and 3.
P was 6 and A was 2 and 3, yeah? So counter example that shows primeness is necessary. Yeah, that's good. P equals 6, and A is 2, and B is 3. So the product A times B is 6. 6 does divide the 6, but 6 does not divide 2. It does not divide the 3. Yeah. Okay, or indeed P is 6 and A is 8 and B is 3. 3 by 8 is 24, is divisible by 6, but the 6 does not divide the 8, does not divide the 3. Okay. Now you can kind of see the explanation for that is the 6 is composed of 2 by 3. And what we're doing here with these counterexamples is we're putting a bit of the 6 in the A and another bit of it in the B, so that in the product you have the complete 6 as a factor. But when you look at the factor, the A and B on their own, you've split the 6 apart, and a bit of it is in A and a bit of it is in B. So the 6 is not wholly in A or wholly in B. Okay. So, but it's only possible to do that because 6 can be broken apart, because it's not prime. Yeah. The definition of a prime number is one which you cannot break apart. So the idea behind these counterexamples you can't do if the number is prime. But we need a proof of it. So here it goes. Now, so we assume P divides AB. Now, we might get lucky, and it may be the case that there's no need to produce any kind of argument, because it might be the fact that P divides A. In which case, there's nothing left to prove. Okay? Because the conclusion was P divides A or P divides B. So if P divides A, we're done. So that actually provides us with extra ammunition. Because if we assume that P does not divide A, basically what we're saying is that the greatest common divisor of P and A is 1. Okay. If P does not divide A, remember P is special, P is a prime number, it only has 2 positive divisors, itself and 1. So the only possible divisors that P can share with another number are itself and 1. Because it doesn't have any other divisors to share and be in common with another number. So if P does not divide A, that means the only remaining possibility is that their greatest common divisor is 1. Of course, what we're trying to prove at this point is we're trying to reach the conclusion that P divides B. Yep, that's what we're trying to prove at this point. If P does not divide A, we're trying to prove that that somehow implies that P must divide B. How do you reach a conclusion that P divides B? You can only reach that conclusion if you've seen the factorization that B is something times P. Yeah. If you see this kind of factorization with an integer times P equal to B, then you can say that P divides B. And as is so often the case in these arguments, this thing comes from the linear combinations, the Bezout's identity. Okay. So from Bezout's identity, there exist 2 integers m and n such that 1 is equal to pm plus na. Okay. So their GCD is 1. We've seen from the Euclidean algorithm that there definitely exists a pair of coefficients that when you form this linear combination, it gives you 1. And this is our starting point to build this required equation. We want an equation with b on the left-hand side. Of course, there's no b's here yet. But because there's a 1 on the left-hand side, you can easily, very efficiently introduce the b by multiplying both sides by b. Okay. Now we have an equation for b. This first bit is clearly divisible by p, because it's got a p in it. The second bit, well, it's got the product a times b, which we've assumed p divides. Yeah.
Why pm plus na equal 1?
Because it's from Bezout's identity, from the Euclidean algorithm. If 2 numbers have greatest common divisor 1, you can run the Euclidean algorithm on them. It'll give you the answer 1. Then you work backwards, and you can generate this pair of coefficients that give you 1. We also proved it in Theorem 2.2. 2.3. Theorem 2.3 said if the GCD, whatever the GCD of the pair is, there will be a linear combination of that pair equal to the GCD. So 4 from Theorem 2.3. Okay. Now we can actually name this integer here. P divides AB. Let's say AB is equal to alpha times P. Then this integer here would be MB plus N alpha. Key point is all these ingredients here, M, B, N, and alpha, they're all integers. So when you mix them up like that, it's still an integer. So this is B as an integer times P, so in other words, P divides P. So that completes the proof, you see. You assumed P divided AB. Maybe P divided A, in which case the conclusion would be true. If P does not divide A, the only way we can rescue the conclusion is if P divides B. And here we prove that if, with the extra assumption that P does not divide A, we get the conclusion P divides A. So that proves Euclid's lemma. Primes that divide products divide at least one of the factors. It's almost, in fact, you could almost take this property as being the definition of a prime number. Prime numbers are exactly those numbers, P, that have this property. That when they divide products, they always divide at least one of the factors. Okay? Because for any composite number, such as 6, you can always play this trick where you can put a little bit of the 6 in one number, a little bit of the 6 in the other number, so that the 6 is present in the product, but it's not present entirely in any one of the factors. Prime numbers, that cannot be done. Okay. Yes?
I still don't know what, I know you're saying it comes from the identity, but
with this
N could be any number.
N could be any. No,
N could be any number, and if you multiply them by primes, how could it be one?
Oh no, they couldn't be any number. Somewhere out there is a special pair of numbers, M and N, that produce the answer 1. I'm saying there exists an M and N. I'm not claiming this is the case for every M and N. Certainly not.
Oh, okay, there exists.
There exists. So that it'd be different if I was saying for every M and N. Yeah, no, you'd be entirely correct. For every M and N, this is clearly not going to be true. So you can produce all sorts of numbers as linear combinations of P and N. But there's there's at least one special pair. In fact, there's an infinite number, but there's a special pairs of numbers out there. Because the GCD is 1, there are special pairs out there, M and N, that we give you 1 as the linear combination. That's the fact we're using. It's the fact that I can form this type of equation for certain N. Okay? Yeah. Okay, so with that knowledge, then we can prove our fundamental theorem of arithmetic. Oh, and we can say as a corollary to this, okay, this refers to products of 2 numbers, but by extension, you can extend the argument to any products of any number. Okay, so if P divides a product A1 times A2 up to times AN, then P divides AI for at least one I. So again, P divides a product, it divides at least one of the factors. And that applies to products of any number of names. So we can now prove the uniqueness uniqueness part of the fundamental theorem of arithmetic. It's a proof by induction. Proof by strong induction. So we let n be a number strictly bigger than 1 and assume for all k where k is strictly less than n, k factors uniquely into a product of prime numbers. So we assume the result we're trying to prove is true for every number strictly less than n. Now we know prime factorizations. We know prime factorizations of n exist. Let's say n is equal to, here's one prime factorization, p1 up to pr, and here's maybe a different one, q1 up to qs. So the pi and the qi's are prime. Q is also pretty much a reserved letter in number theory. You should only really use Q for primes as well. And quite often we use it as this kind of second class choice for primes. If you're already using P's for primes, you're part of the argument and you want to maybe introduce possibly different primes, you would use Q, P's and Q's. So here's our number n. This potentially could be two different prime factorizations of n. Yeah? The notation is allowing that. But what we're going to do is prove that in fact these must be pretty much the same, equivalent. These are in fact the same set of primes multiplied together. Now this implies we can see here that P1 divides n. Okay? And n is equal to the product of all the q's. So by Euclid's lemma, right? By Euclid's lemma, P1 divides Qi for some value of I between 1 and s. Now without loss of generality, which is sometimes shortened to WLOG in proofs, if you ever see that in, I don't know what it means, it's not a strange logarithm function. Without loss of generality, we can say P1 divides Q. Okay, maybe the prime that P1 divides is Q5 or something, but if it is, then we just move Q5 to the front and relabel the Q's so that the one that P divides is at the front. It's just a choice with how you order the prime numbers here. So without loss of generality, for this, we may as well say that P1 divides Q. Remember, this step is justified by Euclid's lemma. If a prime divides a product, it must divide at least one of the factors. So now we can say, so now we consider the integer n divided by P1, which is certainly an integer. N divided by P1 is certainly an integer. Okay? You just forget the factor P1, just look at P2 up to PR. This is a positive integer, but the point about it is it's strictly less than n, isn't it? Because we've cancelled off one of the prime factors. So by assumption, n over P1 factors uniquely into primes. Because that was the induction assumption that we made. we assumed every number is strictly less than k. It's just gone off the top of the screen there. Every number is strictly less than n factors uniquely into primes. Well, here's a number strictly less than n divided by p1. So that must factor uniquely into primes. So the product p2, p3 up to pr must be essentially the same product as q2 up to qs. Just the same bunch of primes multiplied together. They might be mixed up in different positions, but it's really essentially the same product. So without loss of generality, can assume that R is equal to S, and for all i's between 2 and R, pi is equal to Q. So we can assume that they're just exactly the same set of primes. P1, P2 is the same as Q2, P3 is the same as Q3, etc., all the way to the last one. PR is the same as QR. It's the same number of particles. So therefore, when you stick the P1 back onto the front of both lists, remember we've already also proved that, sorry, I missed that, yeah. P1 divides Q1. That implies that P1 equals Q1. Sorry, I skipped over that. How can one prime divide another? Can a prime divide another? Not the only way that can happen is if it's the same prime. I mean, you're just seeing it divide itself. Yeah, remember, primes by definition aren't divisible by anything except themselves in one. So if we have one prime dividing something, dividing another prime, it must in fact be. So the P1 is equal to Q1. All the other P's and Q's are equal. So therefore, this number n does factor uniquely into primes. Because this prime factorization, which looked maybe like it might have been a different one, we proved now in fact they're exactly the same. We've just written out the same prime factorization twice. So this proves the FT. So we've proved all parts of the fundamental theorem of arithmetic. And this really opens up the rest of kind of number theory, and this is why it's called the fundamental theorem. All the other arguments are kind of based on this fact. So prime numbers are special. They're special because they're only divisible by themselves in one, but we've now got an extra reason to think they're special. Every other integer has a unique representation as a product of prime numbers. So it gives you an excellent way to study a general integer. You can study a general integer by examining its own unique pattern of primes that multiply together to give that integer. So we can now speak of the prime factorization of an integer, okay? Because there really is only one. Okay, we'll end it there for this morning. I'll be seeing you again tomorrow afternoon, isn't it?